All right. So today's lecture is, I guess, going to be, it's one of the most important ones because it's what we build off of to start motivating attention, which is obviously like the big mathematical mechanism underlying transformers and the current, growth of language models and things like that. But it should be fairly incremental in terms of like the content and our understanding of what's going on in terms of embeddings and stuff like that. And then the last thing we're going to do towards the end of the lesson is just to we're going to go over going from words to tokens, so actually get to what a token is and just a mechanism of finding them. It is a fairly straightforward algorithm, but it's guys, you mind if you come in late, homie, just grab a seat, please. It is a fairly straightforward algorithm, but it's one that we can test directly, and I do test it directly, so it's good just to know how to do an example of it. But at least last week's video recording covered the topic of CNNs. Well, I'm not going to go over convolution again. I do want to recap and kind of recontextualize the high level idea of where we are in the class and where we are in terms of our techniques of language models. So we started off with the first 2 weeks of just looking at how you get embeddings over here, right? How do you get embeddings? And so we kind of start off by saying, well, I'm just going to count the words that co-occur, and hopefully I can do something like a singular value decomposition, and that'll give me what I need. And then eventually we moved on. We said, well, that kind of sucks because counting is hard and it gives me a really sparse matrix. And so what I'm now going to do instead is I'm going to use this distributional hypothesis. I'm going to say, I think words that are in the center of a context window should be able to predict the other words. And so I'm going to now just train that explicitly in with gradient descent. Okay, and then we went into that and we got word2vec, and we realized that that now actually had this really elegant representation of an embedding space. And so now we had essentially word embeddings that we can leverage for other things. Okay, and then last week we moved on. We said, well, now that I've got word embeddings, how do I get sentence embeddings? And this is the high level architecture we're looking at on the right here. Yeah, we have, all we're going to do is we're going to take our sentence, and instead of representing words as one-hot representations, just this idea that the words are unique, we're going to replace them by these embeddings. Again, either that looks like a linear layer, like a dense layer, just multiplied by a one-hot representation, or we know we can just go and index directly into that weight matrix, and we will get the representation that would come out from that matrix operation without having to do this giant sparse multiplication. So then all we do is we just go and index directly into a weight matrix, and that gives us our embeddings. We're going to look a little bit later today at just exactly where those may come from. So if you're feeling a little bit unsure of that and you just want to focus on the neural network, totally fine. For now, those are pre-trained. I take them out of word2vec and I go and drop them directly in at each point in the sentence. And all I care about now is how do I combine them into something interesting. Okay, now we're going to use a neural network. Last week you looked at a CNN. I'm going to finish talking about the CNN now because the recording didn't go to the end. And then I'm going to move on to recurrent neural networks. Okay, so you would have ended off, you would have ended off around about this slide here. So you finish looking at how you have a sliding window at the bottom with the convolution. So in this case, you have 4 different filters because that's how many nodes you get out at the bottom. And those filters are applied at every point. So you can see over here, that is one set of 3 words that you are applying together. One set of 3 words that you're applying together. And so you're looking for these patterns of combined words. You don't really care where they are in the context of the sentence, but you care where they are relative to each other. So for example, like the cat over here, that's a really, really good pattern of 3 words to notice if you're doing things like sentiment classification, right? You can find a pattern in those 3 words because that seems positive. You're talking about a cat. Most people are positive about animals and so on. Okay, and so we have the sliding window and we just go and look in the sliding window for these patterns across our entire sentence. Why is this not working for me? We go and look across for this entire pattern, and then we get all the different patterns we could care about. So we have one filter that's looking for like the cat, another pattern saying like the dog, another pattern saying hate the cat, another one saying hate the dog, whatever. You're going to have, tons and tons and tons of these. And you're going to let the statistics of the data set decide what exactly those are. And so now we've extracted that. We've done this pattern matching step. and we can go and find these really cool little things in the sentence that we care about. You then pass it through a nonlinearity. Okay, why the ReLU in this case? Well, it's kind of debatable exactly why. We're still figuring out why a ReLU works so well. But one of the reasons is because it's just saying that either there is a positive representation of something or nothing. All right, so your activations in this case are not trying to represent the opposite of liking the cat. You will have a separate filter with that. So either you're positive in the hate the cat kernel, or you're positive in the like the cat kernel, and those two things should never really be co-occurring. Okay, that's the kind of gist of it. So then rarely you can just transform you into this representation where all your activations are positive, and the kernel is now the thing that represents the different like kind of axes of valence, right? It's like whether or not you hate it or you like it, rather than trying to now say that hating the cat is the negative of a like the cat kernel. That's not exactly, doesn't work as well. And it's the same intuition for images, right? You have a kernel that can detect cats. What does the negative of that kernel mean? Either it's the negative physically in the image, like the kind of black outline version of it, or it's ill-posed. So we just use the ReLU to try and say, is something positive propagating forward? So that's all of last week. A very quick little recap on pattern matching. Okay, the convolution operator is only going to be necessary for the first few minutes today. But now we have still a problem, right? And it's the main points of this architecture. We don't just want to get patterns out of our words. What we want to do is get a representation of a sentence, and you still didn't do that necessarily. And so we now have to talk about pooling, okay? So pooling is this operation at the bottom here, and there's two of them. There's max pooling and there's mean pooling. Typically, you're going to use max pooling, all right? And this is a way of being invariant, okay, to the kind of global context. So you would have heard about translation equivariance last week, which means that when I translate the input, there is an equivalent translation in my activations. So if I change where I put the words like the cat and I put it at the end, you will get the same activation out of the kernel. It will just be over there. All right, so spatially it shifts with where the pattern is, and so it is translation shifting, equivariant, equivalent. Okay, now what we're going to get is something that is completely invariant, and that's just going to say, I don't care where it is, I just want to know that my sentence says the phrase like the cat. And if you want that, then all you have to do is go and look through all of the places where that like the cat convolution was applied and take the maximum response from it. And that's exactly what happens, right? So in the first three words of the sentence, you saw it there, then the second, third, and fourth word, third, fourth, and fifth, and so on. You don't really care which one of those is highly active. All you care about is that there is one that is highly active. And so now you're going to say, I'm just going to keep the most responsive version of that. Okay? And you're going to do that for every single one of your kernels. Okay? And again, you have M of them. It's really high dimensional and so on. So for example, once you didn't find the pattern, the last place was 0.2, so you didn't find the pattern. You only found it in this one region over here, and you get 1.2. So all of that, that's all you need to keep out of it. And so you get the sentence representation by the maximum amount of pattern recognition across the entire sentence. So all the possible things you could have looked for, did they show up anywhere in the sentence? And then you hope that by the fact that you're now just representing a lot of these different patterns together, you get a unique representation of your sentence, and it becomes something you can classify. Okay? It is really important to note that this is invariant, so it doesn't represent at all spatially where the phrase showed up. Okay, this is a really, really big assumption. We know it's not necessarily true, but it's happens. Okay, that is the kind of underlying assumption of convolution, is the fact that I don't care where something is. In an image, that is actually really true, right? I don't care if the cat is in the top right, the bottom left, or whatever of the image. I just want to know that there is a cat there if I'm doing cat classification. But in text, sometimes it does matter. For example, we know that object and subject in a sentence spatially fall in different regions. And we will see that this idea is going to come back later on when we do transformers, because we are going to want to track spatially where things happen. And they have their own version of invariance called permutation invariance. Okay, so I do think it's really important that we're thinking in terms of these invariances. And if you go kind of further into ML and research, what these things are called broadly is inductive biases. Okay, sometimes they call them architectural biases. So if you're reading a paper and you see, oh, this new method has a really great inductive bias, it means architecturally there's a limitation on what it can do. If that limitation fits the data, it means you're going to learn a lot more efficiently. If it doesn't fit the underlying assumptions of the data, you're completely screwed. Okay, so here's how this works with convolution. So you're going to have your sliding window in purple at the bottom. All you're going to do with local pooling, or what's called normal pooling, you're going to apply this max operator to a window of two words next to each other. It's the same idea as convolution. You're going to have a stride to it. So you're going to shift that window as you go. You never really have overlap. The same way you have overlap with convolutions over there, you never really have that with max pooling. You usually just shift it in these kind of very separable steps. Okay, guys, I can also still hear you as well, please. So you can then pick how large your pooling is, and then how big the stride is. So if you want to have a three-dimensional pooling or a size 3 pooling, then you want to match your stride so that it doesn't overlap. Okay, this is also used because mainly what the point of the pooling is to reduce a lot of things to try and remember, a lot of kind of representations to hang on to, which is all the words. Then it gets even worse because now I haven't dropped that too much and I have all the different filters to take care of. So what I really want to do is try and get this down to something I can fit into memory and kind of keep processing at larger and larger levels of granularity until I get a really, really big representation of the abstract statement of the sentence. Okay, so here's how that looks locally. So again, all you do is, if in the original example, your window was the entire set of words, in this case, you're just going to look at 3 at a time. Okay, same story. Within this window of 3, the maximum number is 1.2, so that survives there. The maximum number down here in yellow is 1.3, so that survives there. Okay, you don't let there be any sort of crossing outside of the pooling. So for example, the maximum response here is 0.4, because this is not within that max pooling window. That becomes the max for the next representation. Okay, but you can see how you went from something that was 4 rows, at least in the image, and 6 columns, to something that is now 4 rows in the image and 2 columns. So the dimensionality has been dropped nicely. Hopefully we haven't lost too much information in the process. And ideally, if this is a really long sentence, what you're trying to extract out is kind of these, or a really long paragraph. What you're trying to essentially extract out is like, what's the meaning of the first sentence, the second sentence, and so on. That is maybe a heuristic-y way of looking at it. Okay, so that's pooling. Global pooling is what I showed you at the start. It just treats the entire set of words as the window for the max, and you just maximize over all the convolutions. Okay, the really great thing about global pooling is it doesn't care how many words you have. All right, so it can just take all of the words you have, regardless of how long the sentence is, and it always returns the same dimensional output. All right, that's that invariance. So it's not equivariance. It doesn't grow equivalently to how long your sentence is. It is invariant to how long your sentence is. And so you always get the same dimensional response. Obviously, the numbers will change, but you always get the same dimensional response out of it to represent your sentence, regardless of how long it grows. On the flip side, local pooling, kind of, it is equivariance in this sense of dimensionality. And so the bigger your sentence is, the more of these representations you're going to get. Okay, so it's not sufficient if you want to get a consistent size vector out of these operations. It's not sufficient to use pooling. You need to use global pooling. Are we all comfortable with these ideas? Yeah. Yeah, I'm going to speak about that in a second. Yeah, good call. Okay, so that's now this overarching kind of design of our algorithm, right? And when I kind of started the talk today, I said that what we really cared about was going from tokens to a sentence representation. And so now that's ideally exactly what we're going to get, right? So you're going to start with these token embeddings at the bottom, or the word embeddings at the bottom. You're going to do a whole bunch of artificial neural network processing. And again, I would recommend, especially within this course to start, separate those two things out, right? There's the high level big picture, which is how am I going from word embeddings to sentence embeddings and then classifying at the end, all right? And that's just linear regression. You've seen that before. You're just taking a vector input, producing a vector output, softmaxing it, and so you get multi-class logistic regression. Okay? And so that we know how to go from vector to classes. And so that's the whole process there, is now just doing this feature extraction, because I don't always know how to represent sentences, even if I may know how to represent words. Okay, I may have that dictionary, but I don't always know then how to go from that to a sentence. So we're going to learn it with an artificial neural network. Once I pop out with this H vector, and again, that notation is consistent, that H vector, the hidden representation of your sentence, you can then just go and classify it directly. Okay, so we need a model that can produce a fixed size vector for inputs of different lengths. That's the whole theory of it. And so that is why we now do max pooling. Okay, and because each word in the sequence can be thought of as a time step, right? It can be just a generic sequence modeling idea. What you're then really doing is max pooling over time. Okay, and this idea can be used for other things. If you're doing financial data, sometimes all you care about is that something happens in a particular window, and so you'll go and have a convolution that looks for that thing happening, and you'll maximize over time as well. Okay, same exact ideas. You have a sequence, and you're looking for the patterns in the sequence, and then if you find it, you just say, well, it did happen. You don't represent how it happened or where it happened or what time it happened. You just say that it did happen somewhere in the sequence. That's great. I saw the phrase, I like the cat. Okay. And then in this slide now, it's kind of exactly what we just said. Sometimes we don't even know things like how big to make the kernel size, right? Sometimes I don't want to have to choose those things. It's really hard. Maybe sometimes I get a really complicated sentence. There are these things in language called yellow brick road phrases. These are the things you have to understand in their global context before you can understand them, right? So sometimes you'll hear the first 3 words of a 5-word phrase, which sends you down one path in meaning. And then only once I hear the last 2 do you actually understand what's going on, right? It's often used for like humor and stuff like that. I'll look up an example of one just now. Okay, but so you have these phrases that sometimes you need to see in totality before you can understand them. And so in that case, you need to have a really large kernel so that you can actually slide over and find those patterns. So maybe you'll have a handful of size 4 kernels, okay? But then you have your usual size phrases. So maybe in that case, it's just I like the cat or whatever, or like the cat. So then you have kernel size 3, right? Looking for your generic kind of sentimenty kind of statements. And then you have your kernel size 2, all right? And kernel size 2 is doing things like not like. So often negation requires a bigram in this way, right? And as we just pointed out, this now makes the same point of if I'm doing n-gram models, right? I don't always want to or don't always know how big to make the n in those n-grams. And in general, I want to keep it kind of flexible, okay? And so the same idea holds. I'm going to now go look for a bunch of different n-grams. I'm going to have 3 filters now, or yeah, 3 filters now going through my different bigrams, okay? Then I'm going to have a whole bunch of other filters that are now looking for trigrams. So then it's 3 representations. And I don't want to have too many. I know that 4 grams are really, really rare. So I'm not going to have as many filters to it. I still want to have my inductive bias that this is not just throwing the kitchen sink at problems. Okay, so you're still going to have something like a 4 gram, but only a few that you're looking for. And this is really meant to be very specific where it's needed. And then all I'm going to do is take the response of all of my different, quote, n-gram convolutions, and I'm going to append them together, and that becomes the usual H matrix that just goes straight into being classified. Okay? Same exact idea. All we're doing is changing the size of our convolutions, getting the individual representations of the sentence out of each n-gram size, and then concatenating that into a big sentence representation. Okay, last thing then to note is obviously these are neural networks and depth matters a lot, right? Because depth allows us to do new things on top of each representation, okay? So I can't remember if it's in the video or not, so let's see if it is. If I tell you that that kernel, right, is looking at the phrase like the cat, all right, within that red region, what do we call that range that we can look at? What is the phrase for the region of the input that a kernel can see? Yep. Close. Not exactly what I'm looking for. I may not have said it, but let's try. Okay. It's called the receptive field. Okay, so that's the kernel's receptive field. Did I say that in the recording? Okay. Okay, so that's the kernel's receptive field. You then come and do pooling, right? So you get the strongest response to that kernel within this little region, and then you do another round of convolution over here. Okay, so what you're now doing is you're getting a much broader representation of the sentence. So even though this is a convolution with a window size of 2, what it's actually seeing is roughly 1, 2, 3, 4, 5, 6 words. Okay, so as you go deeper and deeper, you get bigger and bigger n-gram representations without having to actually go and do the n-gram convolution kernels, right? Depth gives us that flexibility and gives us that ability to see across the entire sentence without having to just go and throw compute at it, all right? And this is why depth is really, really useful, because it slowly builds up a bigger and bigger picture of our representations, yeah? And you would have seen the same kind of thing last week with so that interpretability slide on convolutions where you look like you had a dog's eye and the dog's leg and it looks all very cursed. But it's a representation of what that kernel is looking for in its receptive field. Okay, and so your early layers of convolution in an image are going to be looking for things like edges and lines, which remarkably is also what happens in a cat's kind of representation of its own visual space. So they've shown this in cats, humans, all different mammals. We all start by trying to process by looking at lines visually. Then you combine lines into shapes, shapes into small objects, objects into bigger objects, and eventually you now have a kernel that can detect the ear of a cat, the right ear of a cat, the nose, its cute little whiskers, its eyes. And so you have one more round of convolution that says, I saw the ear, I saw the eyes, I saw the nose, I saw the cute whiskers. This must be a cat. And it's the same exact story here. You have a convolution that says, I saw the phrase like the cat. I saw a phrase, the red mat. Okay? I saw a whole bunch of these different phrases, and they were all within my receptive field. And so now I'm going to understand that I like the cat and it's on a red mat. I've built up a more kind of expressive representation of this phrase at the bottom of what I'm seeing. Okay? This region here, so this is again the receptive field of that convolution, but because it's now deep, it sees also a part of our input. And so this whole region here is called the effective receptive field of the convolution. Okay, so the receptive field is what it sees on its own layer, and then the effective receptive field is what it sees on the input. Okay, I do expect you to know these words. Please make sure you kind of understand when someone says what is the receptive field or effective receptive field, it means that it's what we're looking at. Okay, does anyone have any questions? We're good? Alrighty, let's move on to today's lecture then. Okay, so that's CNNs, but CNNs have this really big issue, right? Which is the fact that they do not show where the phrase occurred in the sentence. They are translation, equivariance, up until you get to the global pooling layer, and then that makes them translation invariant. Okay? So now we have a problem. We want to get away from that. But I don't know how to get a single representation of a sentence without something like global pooling across time. And so we're going to now instead move to a different architecture, same exact idea. All I care about is this H representation. All I care about is the H representation that says, give me tokens, I'll give you sentence representation. Same exact idea, but now we're still just going to be trying to do this in a different way that doesn't force me to do pooling, that may be a little bit more responsive to position in the sentence. Okay, and so this is a recurrent cell. And it's really important that we kind of understand this before going into the maths. All it is a dense layer of a neural network that has two inputs that get added together. Okay? So all we want to do, let's say it's the same thing as a normal neural network. Over here, you have your hidden layers. Okay, so that would usually be some kind of layer here. These are all connected. Okay, you do a forward propagation, X to H. I want to have a second representation. All I'm going to do is add a whole bunch of new layers, and I'm going to add a new hidden layer, connect them up. The problem is now I have two different hidden layers, and I want my neural network to know about both. So I'm just going to add them. Okay, I now have whatever's coming in through, call it the X inputs, and whatever's coming in through the Z inputs. That now is represented by both. Okay, I have my Z processing pathway, I have my X processing pathway, and now I can just add them together, and hopefully gradient descent just figures that out for me. Okay, because I sure as hell do not know how to merge them, but gradient descent may just be able to see enough patterns that it figures it out. And that's exactly what's happening in the recurrent cell, right? I have some new input, something that I need to update my information with. But I also have some kind of previous representation of my sentence, and that is kind of the other pathway of information. I don't want to forget that, okay? So it acts as a new input to the hidden layer. So you have your input and you have your input. And that is it. That is the whole idea of recurrence, is just, can I take in new information, process it on the input side? Can I take in a representation of my old inputs, all of the things I've seen before, okay? And that just becomes another vector I'm taking in. And can I combine them somehow in this RNN cell? Once you've combined them, you kind of have all the information you need to do some pretty clever things. You can either do some kind of classification off the top of it, or you can kind of go and carry on doing, say, maybe like a word classification, which is where we're going to go to next week. And then you can have a second stream of output, and it's the one we care about the most usually, at least until you get to the end of the sentence, which is this forward propagation of your memory. Okay, so you just output exactly as is your current hidden representation. And you'll see here that this is indexed by T, and it's the same thing, it's H, except now instead of being T minus 1, it's just T. Okay, so what did I do? I took in my input at time T. Obviously, you guys can already see that that's going to be a word. I took in my T time step word. I looked at my representation of everything that came before, all other time points, and I just updated that representation of everything that came before with what I just learned. Okay, so you can think of it, let's say I'm looking at the phrase, I like the cat. Okay, and cat is my current word. Over here, you have the phrase, I like the. And so your neural network is saying, I remember that the sentence said that they liked something. That's really important, especially the liked part. I'm going to hang on to that. Maybe I'm going to also hang on to I, because now I know who's speaking. So I have a kind of parts of speech in this as well. So I have a really unified representation of this phrase on the left-hand side. But now it doesn't know what we like yet. And so it's waiting to find out. And so then it gets time step T, and it now realizes, oh, he likes the cat. I'm going to update my sentence to represent that entire phrase. So it still remembers that it's I who is doing the liking. It still remembers that it's a positive feeling towards whatever is being liked. And now it knows the object that is being liked is the cat. Okay? And so then you can carry on using that representation for all future propagation that comes down the sentence. And so mathematically, this looks like this, right? So you're taking your one input and you project it with a linear layer. Same exact thing I showed you. You get a hidden layer representation for that given word. Okay? Then you're going to take your memory and you're going to do another dense layer. You treat them completely separately to start. Okay? So what does this say? This says, operate on my current input. Do some kind of processing on it that helps me represent it. Okay? You're taking in an embedding at xt, and you're doing some kind of mapping into more of a sentence space. So this takes your word embedding into your sentence embedding space. Okay, that's really important, that now you're changing how you're representing the word. It's not just the word anymore. We know we have representations of words. in the embedding space. What we now have is to project that word representation into how it could possibly inform a sentence. And that's what WX does over here. Then we're going to take our memory as input. And now we're going to do the same thing. All we have to do is say, okay, I have all of my sentence representations before, but now I want to know how to update that memory so that it can be combined with my new word. All right. It's going to tell me how to process my memory, okay, process the previous part of the sentence so that it can accommodate the new information I'm getting. And hopefully those two linear mappings followed by the addition can now get a representation in this sentence space that recombines both. Okay, and again, that addition is just the thing that says kind of combine them and make it into a updated representation of everything we've seen, including the new word. Okay. Why? What do you guys think would happen if we didn't have the WH and WX matrices? Let's say actually, let's say we had WX, but we made WH just the identity. So it just says pull this representation of the past forward, right? Why might we not just want to do that? That seems fairly plausible. Yeah. Correct. There we go. So the whole point that we have this WH matrix is so that it can do a little bit of processing on everything that's come before, which makes it sensitive to time. Okay? As you just said, if all you did was process your new word and add it, okay, addition along that vector doesn't represent ordering. Okay? I can have H plus X and I can have X plus H, and they're all going to give me the same exact vector on the right-hand side. Okay, so an element-wise addition is commutative mathematically, and because of the mathematic commutativity of that operation, you now don't get temporal processing. All right, that looks the same way as if it is roughly, at least in terms of these two vectors, temporally invariant. Okay, so that's really, really insightful. Good job answering that. And so now what we want to have is some kind of additional processing of my memory that again says, I care that that came before, and so maybe I need to update my representation to reflect this fact. Okay, and then XT is just still getting mapped into that same space. Then we go into a tan H activation function, all right, which should be a little bit suspicious to you guys because we just spoke about how great the ReLU is for convolution and how it gives us this representation of positivity only. All right, we can detect things, but I don't need to be able to define what the negative of that thing is. So why might we use the tan H activation here? Yep. Correct. 100% correct. There we go. So I want to be able to, the word is saturate. Okay? So if I'm reading in a sentence and it says, I really, 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 really like the cat, you guys just ignored at least the 3rd through 10th really that I said there because you just saturated. You stopped caring how really I like the cat and you abstracted it towards, damn, this guy really likes cats. Same exact story. My recurrent neural network wants to be able to just ignore overemphasis on things. It doesn't want to keep accumulating information necessarily. All right. It's doing this more on a balance of probability kind of idea rather than trying to express magnitude. And this is something that's unique to the RNN, right? Because the max pooling over the CNN was always within a fixed window, we never really had this unexpected explosion across the length of the sentence, right? We didn't just keep adding stuff for every word. We were combining stuff for every word, which meant that we didn't explode. So in this case, I have to account for that fact. And so I have to saturate at the edge of my my kind of valence, so to speak. All right. Really positive, really negative needs to stop growing very much. Okay. And that is another inductive bias. Okay. I don't have an invariance to tell you about there, but it's another inductive bias you place on this thing. And it's the kind of thing that, again, means that when I say really 6 times or 16 times, the neural network's not going to care. It's going to have roughly the same representation coming out of my sentence. Okay. It will then just keep that same roughly representation so that it groups all of those extremely positive and extremely negative sentences together. Okay, the high magnitude things get grouped, and so it becomes really easy to classify off of them. Does anyone want to hazard a guess? So the tan H kind of, it has a sigmoid shape. All right, it just goes to -1 and 1 rather than 0 and 1. Other than that, it's a sigmoid. Does anyone want to tell me what the problem with this activation function is in general? Say it. Yep. There is a linear regime to it, but you're on the right track. There is this regime, and you do want to try and stay in that bound, right? And you can change what's called your temperature. We'll see that word come up later on, which makes it look a little bit more smooth. So you can have something more of a actual flattened S shape, but you're on the right track. You're on the right track. You're kind of focusing on the flat regions. What's the problem with having flat regions of activation for a neural network in general? Think about training. Okay, there are problems of collapse, and it would come from this underlying issue that I want to talk about. So kind of pull that down one more level of abstraction, right? Because classification is about grouping things. I want the representation for really, really, really like the cat and really like the cat to be as close together as possible if I need to classify sentiment, all right, or degree of cat loving. That's kind of should be collapsing in this H space. Yes. Correct. The gradient will saturate at the edges of this, and so it becomes really difficult to train. All right, you're going to get a really, really slow amount of gradient coming back through back propagation, and so you're going to be making really small updates to your weights. And again, that is something that is there by design, right? That's the same kind of idea as saying I want to saturate on a sentence. I don't want to keep back propagating more information for every time I see the word really. However, I do want to be able to train efficiently, and this does have this problem of saturation slowing down the gradients. Okay, and we're going to see the problems with recurrent networks that really come from this assumption in a second. Okay, but how does this actually play out in the architecture? Also, good job, you guys knew the answers to all of those. Okay, how does this play out in the architecture? Well, all I'm going to do is I'm going to take my sentence representation at the bottom. So again, all the individual words. I have them, I'm told them. I don't know how to do anything with the embeddings yet. So I'm just going to say, well, throw in some word to vec embeddings. And how do I process them into a sentence? Again, I'm going to read them one at a time and just update my memory. Every single time. Every single time I see a new word, I'm just going to say, okay, what did I have before? Coming in this pathway here. How do I update it now with the new information, which is the fact that I am liking something? Okay, there is then one kind of issue, which is sometimes called the cold start problem, and that's more of like a reinforcement learning problem, or a terminology. But essentially, how do I start my representation of a sequence? You don't know how to. So in this case, you're going to start either by representing with some kind of randomness. You can sample that with a Gaussian maybe, or you can start with a zero vector. And this is actually really fundamental to things like diffusion models and those kind of things that we're seeing crop up at the moment, where you're going from something that starts like noise and you're learning how to process it on and on and on, right? So this idea of starting with noise is actually not that bad of an idea. And when we go to sentence modeling next week, rather than some kind of classification task, that's going to be important. But if I have a classification task, maybe I don't want to now bring some kind of variance into it. Again, I want to collapse as best as I can around the distinctions that matter to me. And so I'm just going to have a zero vector. And I'm going to say, just read each word one at a time and map them into a sentence space as best you can. And that first word has no memory. Does anyone want to hazard a somewhat Bayesian perspective at what this initial vector is? Say the word, just the one Bayesian word you know. There we go. That is effectively a prior on my sentence or a prior on my hidden layer. Okay? I can inject anything I want into there that will allow me to carry some kind of information forward. All right, so if I wanted to have a representation of a whole bunch of information that came before, let's say all of Harry Potter up to the last 10 pages, I want this model to now remember so that it can conclude for J.K. Rowling because her last sentence sucked. I can go and try my absolute best to design a vector here that represents all of Harry Potter. Okay? And I can inject that in. And now it will know those things as long as it's sitting in that same sentence representation. Does anyone want to say, and this is very important for the next slide, so let's try. Does anyone want to say why that sounds ridiculous, but say it mathematically? Take that intuition of why representing all of 7 books minus 10 pages into a single 4D vector. Why does that sound silly? Yep, online.
It wouldn't be silly because there's too much information to be represented just by four dimensions.
Correct. Exactly right. There we go. You run out of dimensions, okay? So while you may, yes, be able to mathematically define, let's look at a 2D space. While you may be able to mathematically define that representation, you have a space of all 7 book series to represent, okay? So maybe Twilight plus some other young adult novel that I don't know about. And that's all got to sit in this latent space somewhere. Every possible configuration of seven entire books worth of information is now sitting in a 4D, or in this case, a 2D vector. So if I want to now go and represent the exact instantiation of Harry Potter, I'm going to have to stick it right over there in a cluster of other potential Harry Potter books. It's going to become exceptionally difficult to decode out of it. All right? That is going to be really, really hard to represent. And if I have a little bit of noise and I shift it even slightly up to right over there, now I have an entirely different representation of my knowledge. So it's not the fact that a real number line can't represent an infinite amount of information. In theory, you could take the real number line, go down to the 1000th decimal and just squeeze everything in. All right? It is a question of computation and retrievability out of that representation. All right. And again, it's important. I know like these kind of, it's a bit wordy today. It's important we think in these terms because this, even now when you're prompting GPT, this intuition that it's trying to squeeze representation into a context window, which is some vector space, that helps you. When it goes and it says, okay, I've spoken to you for 2,000 tokens or 20,000 tokens or whatever it is, I'm going to compress my memory. You know why it's now trying to do that. You know that that compression shatters the space and drops a bunch of these representations and makes it a little bit more spread out over here. It makes it easier to retrieve. And you will then understand that a hallucination is just when these 2 bits over there become too close to each other. Okay? The intuition grows, and we will start to see how it comes out a little bit more explicitly in that architecture as we go. But the roots of these problems can be found in what we're doing here, okay? We're not going to be recurrent for very long, but we can keep understanding that remembering all of your prior context is hard. Okay. So give me 2 minutes and then I'll wrap up here and then we can take a bit of a break and, I don't know, get coffee or something. So here are the problems with recurrence. Okay, and you've said them all already, so we can go nice and quick. vanishing and exploding gradients. So you have lots of matrix multiplications. Either they're going to blow up. If you use the tanh activation, you can combat this a little bit, or they're going to diminish, and the activity going through the network is going to end up becoming really small. Okay, so you either go away from the zero representation, and you kind of don't really know what you're doing. You're getting a lot of conflicting words, and so you kind of oscillate back and forward in how you're forward propagating this information, and then that's going to make credit assignment really hard. Or you're going to explode and you're going to get 10 realies in a row, and now you don't know how to represent that many realies. Okay, that goes to the second problem, which is the credit assignment problem. And when I forgot a word 2 weeks ago, this is the phrase I was looking for, credit assignments. So credit assignments is a known hard problem. This is exceptionally hard because you can't know where a word came from when you get something wrong. Okay, so when you misclassify off of that vector there, did you misclassify because you represented the mat wrong or the cat wrong? I don't know. It came through this vector channel. It came through my last round of recurrence. How do I now say, actually, that was a problem with this channel rather than that immediate one there? And so what it's going to do is it's just going to back propagate. It's going to say, well, both of them forward activated. Both of them have representation here. And so I'm going to give some credits to both. Okay. And so maybe you hate maths and you really love cats, and now you have a problem because you just got your classification wrong. Your classification is saying, I'm really happy with the sentence, but actually you should have hated that sentence, okay? And the reason you hate the sentence is because you're talking about maths and you really dislike those, but now you're also going to say, oh, Devin must dislike cats, which is completely false, okay? And so now there's a problem. You get conflicting information. How do we get around this? We do the dirty machine learning thing. I show as many representations of these sentences as I can. And hopefully, if you speak to Devin long enough, or if you attend his lectures, you will know that he indeed likes cats. And you can start to disentangle that. And hopefully, you can speak about cats with Devin without seeing the word mat all the time. And then you'll be able to see that statistic. And you'll be able to say, oh, when I have with the word cat alone, it's positive. And when I have the word cat and mat, now it's really bad. Okay, so it must be mats or that combination of the two that Devin doesn't like. But at least cats in isolation, we're happy. Okay, and so credit assignment comes out from this overwhelming amount of data. And again, foundational to what we're seeing in the field at the moment, right? You've probably all heard slightly of neural scaling laws. We will lecture on it later on. But we know that as I get more data and bigger models, I get a reliable improvement in my transformers. GPT-5 gets better than GPT-4. Is so we talk about it, okay? Same exact idea. The more data I show you, the easier it gets to do credit assignment. I get these more nuanced bounds in my representation, okay? And again, the only thing that transformers did that was really, really insightful, aside from the attention mechanism, which is extremely elegant, we'll see it in 2 weeks, is be really good at churning through lots of examples. It is as much a success of engineering as it is of concept and mathematics. Okay, and then lastly, what we also just said earlier online is we have a fixed size vector that needs to represent all of the stuff coming through. So if my sentence gets really, really long, to the extent that it can be 7 books of Harry Potter, well, then I'm going to have to now squeeze 7 books of Harry Potter into one latent space. But if my training data is all short sentences of roughly 10 to 20 words, I'm a lot happier. That's easier for me to represent in the same sized vector. Okay, and so you have this fixed size vector problem where we're always trying to squeeze more and more information into the vector without ever having any mechanism to just hold on to the important bits aside from this weight matrix. But that is a really difficult learning problem for that weight matrix because of credit assignment. So these two things together mean that it's really, really, really difficult to represent long sentences. Okay, I have to squeeze it into a fixed size vector where it's very difficult to know what I must hang on to. That's the phrase. Those two things together. So if I asked you in a test, what are the 2 primary problems with the RNN? I would accept any one of these 3 answers, but the 2 I'm mainly looking for is the fact that I have to squeeze everything into a fixed size vector, Devin. And so now if the sentence grows, it becomes hard to represent all the information efficiently. And it's really difficult for the model to even learn how to track its memory because of the credit assignment problem. Okay. Write a 20-mark essay on that. Okay. See if there's a good point to stop. There is. Give me 2 minutes. Okay, then the same story. I want to have layers and layers of processing to my neural networks. And so what do? We stack them. Okay. And then it's important, especially as we keep going in the next few lectures, to track the pathways of information through the model. All right. This becomes really important. So keep practiced at this. Okay. This is a good way to start thinking these terms. You want to look at the information flow through these architectures because it's designed really deliberately. Okay. And so here, if I'm looking at this representation over there, it can have the current word being processed. It has its own memory. So we know that it's doing exactly what the RNN is also meant to be doing, right? It's taking my current word, it's updating that information, it's putting it into a sentence representation. It's also hanging on to everything coming from the left. So it knows all about the sentence. But on top of that, it also has this pathway here, okay, which is all of the sentence representation that came one level down. So this knows all of that, okay, not just from its own processing, but from the layer down. And so you can have these repeated processing points of processing where you're constantly updating the word representations and how you're accumulating them in sentences. Okay, and so maybe this first level is doing some really basic things. Okay, maybe that's just trying to hang on to things like sentiments and nouns and objects in my story. And then this layer is saying, well, I have those representations. I didn't have to pull them out of the tokens anymore. I'm getting the more abstracted representation for free, okay, from my earlier layer. And so maybe now I can do something a little bit more complicated. Maybe now instead of remembering the characters in my story, I can start to represent their actions with each other. And maybe the next layer will start to remember the narrative of how their actions link together. And that is how the depth in the RNN plays out, right? You get more and more detail in terms of what the actual words are saying and how the words interact. Okay, and then lastly, because of the problem with trying to squeeze things into a fixed size vector, we have an issue where things that come on the left early on get forgotten. Why? Because they have to be multiplied by more and more matrices. Okay, this word here in my original representation gets processed and then it gets multiplied by a matrix, multiplied by a matrix, multiplied by a matrix, multiplied by a matrix. And so by the final word, it's been multiplied and updated 6 or 7 times in this same sentence embedding space. Okay, and so it can drift. It's gonna get forgotten much easier than this token over here is going to just get projected into the sentence layer. That's one level of projection, and so it's going to be a lot more precise and a lot more accurate. Okay, again, it is a notion of computability. And so what ends up happening is the early words get forgotten, they drift more by each matrix multiplication. And so I have a problem where I'm dominated by things that come on the right-hand side. And so again, ML people are really kind of simple sometimes. They just said, well, why don't I process the sentence from right to the left as well, do the exact same thing, and then just combine their H representations. That is called a bidirectional RNN. And the whole idea is now this vector is dominated by what comes, this one here, the red, is dominated by what comes later in the architecture. This layer here is dominated by what comes earlier in the sentence. And then the middle stuff, well, hopefully that is a mixture of both. And so I'm not forgetting that representation on either side, but you still end up with this problem where the middle of the sentence is now the thing that is dominated the least. And so, you know, there's always going to be a trade-off, but hopefully you haven't forgot anything really badly. Okay. You still have a good mix of information across your whole sentence. All right. We will see in a few weeks how attention actually just gets around that completely. All right. That's where we end with that. Does anyone have any questions? Okay. Let's take a 15-minute break and we'll come back and we'll end off with something pretty light. Guys online, can you hear me? Cool, thank you. All right, let's get started again. All right, does anyone have any questions to ask about any of the stuff we've covered? CNNs, why we're doing any of these things, RNNs. Are we all relatively comfortable with what's going on here? Okay, seeing a few nods, that's good. So we're now going to just speak about the last kind of bit for today, which is word embeddings and where exactly do they come from and how do we go from word embeddings to actual token embeddings? Very similar thing. So word embeddings, then we know that we need them to start these two processes, right? Whether you're using a CNN or an RNN or anything else, we need to be able to throw that into the neural network somehow. So where do they come from? And there's three main ways. You can either train them from scratch. And what that looks like is exactly the same way when we were doing word to vec. You had the embedding layer or the encoder, but let's say the embedding layer, and then the decoder or the context embeddings. Instead of having embedding to context embedding, we're now just going to have embedding to the rest of the neural network. Okay, so you just throw away that decoder. You now have all of the CNN or the RNN or whatever you want, and you're just going to train it the exact same way. It's just gradient descent. Okay, can I ask anyone in this room, let's get our intuition about tokens up and running again, or about embeddings up and running. Why do you think it may be difficult to train embeddings from scratch if you're doing something like classification? Okay, so a reminder there that word to vec is really hard because you have this mapping from sensor word to 4 different context words, right? It has to predict another word and it's getting conflicts of information, right? It's getting 4 different labels for the same input. And we said that that difficulty there is actually why we get good word embeddings, right? It's that distributional hypothesis. Does anyone want to say why training embeddings from a classification task may give us not very good word embeddings? I hope the guys online are feeling as awkward as we are in the room. Someone want to have a guess? I gave you the answer. I said that word to vec was really hard. So why might this not give us good word embeddings? Yeah. No, you're reading ahead. Why training from scratch sucks. I'm gonna have to turn my camera on and like stare directly into it so they also get uncomfortable. Okay, so let's be clear here. We're not taking a word to vec at the moment. What I'm asking is when I have to back propagate from a classification through my neural network into those embedding layers, right? And again, that's a one hot for each word multiplied by a linear layer, or it's just indexing into that matrix. Same thing. Embedding layer is when you index into the matrix. Why is just indexing into this matrix of representations for each word? Why might I not get good representations for each word when it's back propagating from a classifier than when it's back propagating from the 4 different context words word to vec has to pick? Yeah, fantastic. Pull that thread a little bit more. Why less information? What's the less information there? Okay, that's the right word. Again, like let's formalize that intuition. Your intuition is 100% correct. You know what you're talking about. Let's just pull it into something a little bit more wordy. Full. Okay, So what you're saying is that classification is a lower rank problem. It's really easy to classify if all you need to know is roughly the notion of a cat or roughly the notion of happiness, right? You don't even know the difference between happy and ecstatic or cat and dog if all you're doing is animal classification, right? So there is this collapsing of the information coming through a classifier. Whereas if I have to project to 4 different words and I have to be really specific about those words, that is a lot of pressure and a lot of detail that I now have to use and embed into my word embeddings to try and do that task. So while the overall process seems more complicated, right? While I have to go from words to sentences in this task, because I'm filtering through a sentence representation, there are a lot of different word embeddings that would still be consistent with a good sentence representation to get the right classification. Okay, so it's thinking in terms of this rank, so to speak, of the problem, or just the actual scope of the problem, and that your intuition was perfectly correct there, right? And so just because I am training a bigger problem does not necessarily mean that it is going to be as informative to the lower levels of this architecture, okay? And so that's why we don't want to train them from scratch, is because I want to understand the difference between happy and ecstatic and really happy and so on. I just don't want to now have word embeddings that are consistent with a general notion of pleasure, okay? And so the second two that you can say, if you read ahead, is now we know that word to back and glove are really taxing on the word embeddings, okay? That's a really difficult problem. And so it's going to give me really good word embeddings. And so I can just take those as pre-trained, and that's what I've been saying this entire time, all right? You just take that encoder layer and you start it off as that. And sometimes you won't even kind of backpropagate, you'll just use it as if those are your word vectors to start. Or what we're going to do is you're going to take them, the third option and the one that most people use, is you take something from a glove or a word to vec, all right? So you have these pre-trained word embeddings, so the details are there. And then we're just going to keep back propagating through the classifier so that we update those word embeddings to be a little bit more task specific. All right. So if I'm doing sentiment classification, I don't have to really care what genre of the book we're in. All right. So now my embedding for the word dragon at the bottom here can maybe move more towards an embedding that represents the sentiment, which is fear or whatever, if we don't like dragons in fantasy books, rather than trying to now represent the actual notion of a dragon and the fantasy elements and all the stuff that goes with that, right? We can now start to be a little bit more specific to the task with our embeddings, but we still have sufficiently separable word embeddings to get a lot of detail out of it, okay? And again, there's something foundational to this idea here. The more difficult the task, if it's trainable, the better the model, all right? Again, this is foundational to what we're seeing in the scaling of LLMs, right? We took the entire internet and we told it to remember that, rather than taking just Wikipedia and said, remember that, right? Much harder task, way more data, way more details, way more variance. Turns out, if you have an architecture that can accommodate that variance, it can handle that much data at a kind of numerical level, you will actually get a significantly better representation out of it, and one that now understands kind of, let's say, the world understands, quote, the world better for it. Okay, so the harder the task, the better the representations you get. And so unfortunately, in a lot of cases, having classification is not hard enough on your early layers. It may be hard enough on the sentence, the recurrent stuff. That may be difficult. Okay, so there's 2 different ways we can do this. You either take your training data that's just the stuff you want to classify and you run on that. Okay, and you train a really small specialized neural network, but it's not very adaptable and it's domain specific. Or what we can do is take the entire corpus of the world and just take Wikipedia, train some kind of massive word embeddings, and then fine tune that to our task. So now we have a really rich representation of our words, and we have a far bigger dictionary to handle new stuff, and then we can just adjust it to be a little bit more specific to our needs. Okay. In the past years, the project trained transformer model and fine tune it to do a literature review in a medical space. Okay. And so what we did was take, that's good. Guys online, can you still hear me? Yeah, okay, so it's the tablet. Give me a second, I'll be back. Oh, wait, but it's still working. Okay, we're back. Of course, that happens today. We have 20 people online. And it is actually still not showing up. There we go. Okay. All right. And so then the idea here is that we want to challenge our word embeddings. So we're not going to train from scratch, right? So we're not going to have enough data to really get good representations of words that way. The task isn't going to need us to separate words too specifically anyway. And so what we're going to do is we're going to train something like a word2vec. So you get the representation between words, and then you just fine tune it on your specialized data, and you get the best of both worlds. And again, that can look like taking every paper, academic paper between archive and bioarchive, and you train on that first. So that now you just have a general notion of academic language. And then afterwards, you fine tune on bioarchive. And then afterwards, you fine tune on cancer literature, which is the thing you want to do your literature review on, right? And you have the staged curriculum that gives you the words and gives you the really hard task up front. And then you slowly become more specific to the details, all right? This is often termed an anti-curricular, all right? When you start with the harder task and you form a stage of tasks that get easier and easier over time, okay? Sometimes it's the right way to do it, okay? Other times you want to form a curriculum where you show it easy stuff first and then go more and more challenging, okay? Oftentimes you want to use an anti-curricular when you want something very general at the start. And so this is a version of transfer learning. We're going to look at this in detail in like kind of a month and a half or so. It's towards the end of the class. So what you do is you learn stuff in one space, and then you transfer that knowledge to your new domain. Okay, so you go from transferring a general amount of information into your task-specific domain. So it's just how you construct your data sets and train in order. Okay, we also want to make the task more difficult. And so we can do data augmentation. This isn't so common anymore because we get lots and lots of data from the internet, and that's, you know, about as augmented as we're going to get. I'm going to ignore that for now. Okay, but in the past, what we had to do is we had to increase the amount of data we had and give it more and more diversity, all right? So on an image, we would start with one image of a cat, and we would rotate it, we'd flip it, we'd zoom in, okay? If you've ever seen SimClear, right, that's a very, very weaponized version of this idea, where what you're saying is I want to augment an image, but without changing its representation. I want all of these things on the right-hand side to represent the same way as the image on the left. Okay, I don't care that I can't see the cat's top right ear in this case. You know, I know that top right fluffy ears are really important for detecting a cat, but I still want it to be able to detect a cat from the rest of its little fluffy face. And so we're going to now train it to do that. Okay, and so if the architecture was previously relying on its right ear to classify it, now it can't do that. It's going to learn a more general set of representations. The same is true in text. We can just do word dropout. So what you do is you take your sentence and you just replace a few of the tokens or a few of the words in the sentence, okay? You can have this U and K token, which stands for unknown. So you just remove a few of the words and you force it to do the task on the remaining words, okay? Or you just go and replace it with random words, which is going to inject that little bit of noise. It's the same idea as word2vec, where you have to predict 4 different things and there's now a conflict in that information. Same idea. I'm adding a little bit of conflict so that it makes it harder and makes me rely on the important aspects of the sentence, which is now the fact that there's a cat and it's cute. Okay, this is very much the same linguistic notion as occluding aspects of an image. Okay, You could do something a little bit smarter, which is going through a thesaurus or using some kind of external knowledge to replace synonyms in the sentence, okay? So the movie about cats was absolutely great, becomes the film about cats was certainly great. You added synonyms, and so now you can get 3 or 4 data points for the same initial text, okay? And so you now get more and more representations of the words. And again, using the distributional hypothesis here, you can start to actually collapse those word representations to be a lot more specific, and you can start to pull out a greater variety of representations from it. Okay, you can take this to a really intense example where what you do is you translate from English to another language, so Russian, for example, or Japanese, and then you decode it. And every time you do a cycle of encoding and decoding, you're going to change the sentence slightly. And so you have one sentence, which was the movie about cats was absolutely great. And then eventually becomes the cat movie was just great. Movies about cats are absolutely great. And the cat movie is really nice and the cat is cute. You get different phrasings of the same sentiment each time. Okay? And that's just because translation is not cycle consistent. Okay, this is the same way as doing something like rotating the image. You know, you kind of encompass the same information, but now represented in a kind of different way. All right? So geometrically, it's changing in a sense. Okay. Everyone happy with that? Those ideas of representations and things like that? Okay. A lot of the times, and we're going to speak about this a lot more later in the class, which is why I just kind of stick this at the end here. A lot of times we want to try and understand what the convolution filters are doing. I actually referenced the slide earlier. I forgot that it comes at the end of this one. So in this case, what we're doing is we're trying to see what visual patterns activate a convolutional layer the most, right? And so when we're stacking the convolutional layers, you can do the same thing with the recurrent net here. When you're trying to stack the convolutional layers, early on, you're going to have these really kind of cursed representations that look just like edges and a little bit of texture. So you can see the kind of ribbed texture over there. None of these images make sense in their own right. They're just very kind of intense geometric information. As you go to the deeper layers of a CNN and you try and kind of maximally activate that neuron, again, this was an algorithm that did this kind of like maximum kernel activation algorithm, you would get a region that included something like an eye. All right. And so you would get that information that eyes now matter. And the way that that happened was you combined a bunch of edges. You combined that edge and that edge and that edge and that edge, and you combined a convolution that was looking for some fur. And so now you have these earlier convolutions that can find edges and fur and different texture, which means that when I convolve over those higher order representations, I can start to do things like look for an eye, look for ears, look for maybe a really weird object of a leg, and so on. All right? Always a little bit cursed, but certainly more recognizable. And as I go deeper and deeper, I'm now combining not edges, but I'm combining eyes, I'm combining ears and legs. And so you can start to then get things like a really cursed looking deer or a bulldog or a clock and so on. Okay? And so you start going into these higher levels of abstraction. And the same idea is true. GPT has plugged this problem, but up until a year ago, you couldn't ask GPT to draw you an image of a clock with a specific time, okay? Because of this problem, because getting that fine detail from low-level representations is really, really hard. There was also a data thing that we will speak about, which is also why I couldn't do that. But it's kind of a fun example of how GPT can do some really simple failings. I urge you all to try it, by the way. If you want to go and ask GPT, draw me a picture of a clock and set the time to be a specific time. Just don't ask it to do 10 past 10. Then it will actually struggle still sometimes. It's a lot better. Okay, and so how do we do this in a text way? Well, all you're going to do is go into a layer of your convolutional neural network, let's say, look at each of your filters, find the one that gets the most activity. So again, looks a lot like the max pooling. Let me not use green here. Looks a lot like max pooling already. So you go and you say, well, where was that maximum activation on my kernel? And you go and you look where it was, and you trace it back down the kind of architecture, and you can see that it says, well, it's sitting on top of I like that, or like the cat, right? So all you do is go and look for where spatially, or in this case, temporally, your convolution was most active. Okay, and what you'll find is that a lot of the times a convolution is activated by this roughly the same 4 n-grams. All right, so it's doing this kind of initial filtering of sentiment. So saying things still work perfectly, it works perfectly, it proves invaluable, near perfect, still working great. All of those 4 grams, all of those phrases will still activate the same kernel, and this result is taken from a specific paper on text classification. Okay, so again, this is remarkable. It's collapsing all of those things into roughly the same representation. The problem here again is that because it's collapsing all of these to the same representation, understanding any one of those words becomes harder. All right, so that's also why we don't get great word representations from a immediate classification model. Okay, because it's this collapse, and now we don't understand any one of those words perfectly anymore. Okay, any questions about that last little interpretability bit? We will come back to interpretability a lot as we go. No? Okay, last thing for today. All right, so we've now moved on and we've said, well, we want to understand our tokens or our words, right? So the last few minutes we've looked at how do we kind of get the words. Either we can pre-train those embeddings or we can do them directly. We want to try and we can do some interpretability on those embeddings, right? We saw word2vec, you can do the arithmetic on them, or in a CNN or an RNN, you can look at where those words are embedded in the kind of bigger sentence space and look for the maximum activity across your kernels. So we can start to get to an understanding of what the tokens are doing or the embeddings are doing. But we have one remaining problem, which is the fact that I'm limited by a dictionary. Okay. And so the size and the number of words that I have is limited to the number of words that I've seen in training. And I now need to have what's called an open dictionary. Okay. I don't want to be limited by that. You'll see that word come up a lot at the moment in things like robotics, because what we want in robotics is to have an open dictionary so that it can handle a bunch of different objects in its environment. Okay. Often is then called open set or whatever like that, depending on the task it's doing. But this idea is that I don't want to be limited by the objects I've seen. I want to be able to understand new objects, 0 shot. So, okay, so 0 without more data, shot as in I can handle it. Okay, so let's move beyond words. So usually we're splitting text by white space, and this works well in many cases, specifically English. However, African languages, for example, a lot of them are what we call agglutinative. We saw that word in the first lecture. You can make new words by combining earlier ones. So if I'm splitting by white space every time I see a new word in Zulu, I'm just going to be adding a bunch of words. It's going to grow enormously, and we're never going to actually understand what's going on, right? There are examples still where GPT cannot tokenize the phrase, I like the cat properly. I'll show it to you at the second last lecture or the last lecture, all right? It cannot tokenize that because of the agglutination. It tries to handle the words all as one big mess. All right. Whereas English, it's great. You separate by white space, you get the words out. It's fantastic. Okay. So number one, not going to be true for all of our languages that you can just split by white space. But this means that we're also having a predefined vocabulary. Okay. And again, agglutination, that's not just the style of that language. It's not limited to a predefined vocabulary in any sense. Okay. And so words not seen in training will just ultimately be replaced by an unknown token, and that is going to be semantically meaningless. Okay, there is no way to get a good unknown token embedding that is actually informative about what it should be saying there, right? All it will actually do is represent an embedding that says maybe guess this word. That's the nicest thing it can do for us. And so this means that we're limited in our processing power. So how do we move towards something a bit more general? Okay, so let's say I show you a new word you've never seen before. And again, let's say we're doing Zulu, where it is possible to just give me a new word that is completely well defined by the arithmetic of that language, right? We have a comment. Oh, no, not Discord. And so in this case, what do? Well, the best thing you can do is look at the new word you've never seen, look at pieces of it and say, well, maybe I can make sense about what the word is saying as I go along. All right, maybe I can think around the fact that I know what the word cat is in cats, so I just need to figure out what this S is doing at the end of it. All right, maybe that'll help me. But at least I understand that the word cat is there, and I've seen a cat, so maybe it's this cute fluffy thing. And I just now need to update my understanding that it's multiple cute fluffy things. Okay, So word level tokenization, not what we want. You don't want to just split by white space and say that each word is your representation for an embedding. We want to have embeddings that are a little bit more general, okay? And so we're going to tokenize, so the pieces of words in our processing stream, okay, they are called our tokens. Sometimes the tokens are the words, but ultimately these are just the things that you embed first, right? So they can be more general. You've seen already an unknown token. Okay, that's not a word, but it represents something. A lot of the times you'll have tokens that represent the start and the end of a sentence. Okay, a lot of times lately we also have context tokens, which do things like say a personality for a model and so on. Okay, so we want to move towards subword level tokenization so that I can do exactly what we just described here in the model, which is say, can I look at the pieces of the words I have seen and do my best to make sense of it as we go? There is a notion, it's not general, there is a notion that we want our tokens to align to the morphemes, okay? Because we said at the start, morphemes are the lowest unit of meaning in our language, okay? So these tokens are going to be the lowest unit of meaning in our architecture. It's really great if those two things line up really well. It's not necessarily always going to be true, but it is great if it can do something like that, all right? And so if you ever then encounter an unknown or a rare word, you can just do your best to try and encode it as a combination of the pieces you have seen. And this is exactly what BPE, so it's called byte pair encoding, tries to do. So BPE is an information theory algorithm. It's not unique to linguistics or language, but it turns out it works really, really well for creating these tokens. And so all we're going to do is we're going to take every single word in our dictionary or in our training set, and we're going to split it. And we're going to try and find these frequent pairs of symbols that go together. And we pair those up and we make those into one thing. And then everything else is left general to be combined later on. I'm going to show you that example now. Okay, so the main idea is search through your current list of symbols and find the most common pairing. You're then just going to merge that pairing into a new symbol. And you just iterate this process as many times as you care to. It is important to note there are two phases to this. Okay. And in a test, I may ask you to do either one. I may ask you to do both. So there is the training phase, which is where you find the symbols to merge. Then there's the inference phase where I give you a whole bunch of new text and you go and replace it with these merged symbols. Okay? So we can look at the pieces separately. So how do you train the thing? You're just going to take a corpus of text, not necessarily the same data you even want to train your model on. It can be any sort of text. A lot of the times you'll see again, if you're using GPT and stuff, that you'll use a pre-trained tokenizer. There's the GPT tokenizer and there's GPT itself. They're not trained on the same data. The GPT tokenizer is based on BPE, and they just kind of showed it a whole bunch of other words. But the training pipeline for training a model and training a tokenizer do not need to be the same thing, right? You do not need to show them the same data. And in general, you will pre-train your tokenizer so that you can then just move straight on to training your embeddings in your model. Okay? Please do not confuse the tokenizer with the embeddings either. The tokenizer is what gives us the low-level symbols. The embedding is then the mapping into an embedding space for those symbols, right? So it's then how do I represent the tokens that I already have semantically? Okay. All right, and then the output of this process is going to be a merge table and just your vocabulary of tokens, right? I'll show you an example now that will be really clear in a second, but it's just a table that tells you when you get a new table, when you get a new set of text, go look into the merge table and just find the pairs that should go together. And on top of that, we then have our vocabulary of tokens, which is essentially your dictionary, right? It's your vocabulary of words. If you're completely separating by white space, that's exactly the same. Okay? So your merge table says which characters should be combined, and vocabulary is just literally the tokens that you know how to handle. Okay? So to begin with, you're going to split your text into the characters, and then iteratively find the characters that should be the highest co-occurring pairs, and merge that into a symbol. And you find the most frequent pairs, you just keep iterating on that. All right, most of this detail is here for you to study, so let's look at an example. Okay, so we're going to assume this is our corpus. Again, a really simple corpus for us to deal with, but that's our corpus of text. So you have 4 versions of the word cat, 5 of the word mat, 2 of mats, 3 mate, 3 ate, and 2 eat. Okay, that's the data set we have to train our tokenizer. And so what are we going to do to start the first step of this process? You take all of your words and you separate them by their letters. Okay? And you now go and count the occurrence of each word. All right, just counting the occurrence of each word means that it's just slightly easier to count because you don't tokenize across words. All right, so all we're doing is counting when these two letters appear next to each other, the two symbols appear next to each other in the same word. Okay, you can read it on the right hand side there. So M and A appear the most. No, A and T appear the most in this example. M and A appear the second most times, or 10 times. But A and T appear in every single data point we have here by design. So they appear 19 times. Okay, all we did is went and said, this is A and T, so I'm going to count there, A and T, count there, A and T, count, and so on. So you end up summing down the list. Okay, looking at M and A doesn't appear there, so we don't count it. M and A appears there, so it's 5 occurrences, 7 occurrences, 10 occurrences, and that's how you get to 10. All right. So you're just counting the number of times the two symbols end up next to each other. You find the most one. So A and T. You've initialized your merge table. So what you're going to do is you're going to say A and T now becomes a new symbol beta. Okay? A and T was the most frequent pair. They are combined into a new symbol, and that symbol is now put into the corpus wherever it shows up. Right? Every occurrence of A and T is replaced by beta. And you just cycle on this as many times as you care to until you think you've converged. Okay, so what's the next highest count? Well, M and beta appears 10 times, beta and E appears 6 times. And so what you're going to say is, well, M and beta next to each other goes into my merge table. Okay, and this is important. The merge table is ordered. Okay, you have to read it top to bottom so that you first look for places to inject the beta, and then you can find the betas after that. Okay, this also means that BPE is deterministic. Okay, it always tokenizes, tokenizes the exact same way. All right, so you can use one of the new symbols in subsequent combinings. Okay, and so then finally you can merge C and B, since this is the new largest combination. You can go and check that, and so we get C and beta, and so now we get mu, and you end up with your vocabulary or your kind of words on the left-hand side and all of your different merge tables. And what you will notice is that the word cat and the word mat became 2 new symbols. Okay? And so now that symbol gets put in to get embedded into the model, and it turns out that that looks exactly the same to the model as the word cat would have. All right? If I said I'm going to tokenize around white space and you got the word cat, that's fantastic. You now tokenize the word, you go and embed the word cat. Same story. I have a sentence, I loved the mu. I really, really, really like muse. Okay? And so now what you're going to do is go and embed the symbol for mu instead of cat. All right? Same for alpha and mat. Okay. Then lastly, for inference, what are we going to do? We've trained the model, so we have our merge table. Okay, and all the different vocabulary we can handle. And so now we're going to go down this merge table and look, when I get the new text, I split all of it by its letters. And when every time I see an A and a T, then I go back to the top of my corpus. And I go and I look, every time I see an M and a beta, I replace it with alpha. Every time I see C and beta, I replace it with the mu. Okay, and I can then handle completely new text every single time. All right, now at least if it is cats, we can finish this without the slides anyway, but now at least if I've seen the word cat, I have a symbol that's been tokenized around the word cat. I can understand that as a concept in its own with this mu character or beta or whatever it was. And then all I have to do is try and understand whatever comes after that in my text, right? But now we have an open vocabulary because what I'm tokenizing is these symbols. It is not the words. And these symbols can then start to be combined together afterwards in new flexible ways. Okay, so these are subwords, all right? So for example, 8 is still then represented as 2 different tokens, but now at least it's beta E, and so you can now try and embed that together. And so maybe the fact that there's a beta there helps you later on. It's hard to make a great example of this because this does require huge amounts of text and you will tokenize a lot. All right. So it is a bit of an intense process, but it is deterministic because you read from top to bottom of your merge table when you tokenize new text. Okay. Does anyone have any questions about this? Is this process easy? Could we all do it on paper on a small example, both training and inference? Great. Cool. Thanks, everyone. That's the end today. I'll see you next week.